Hi again. In this lecture, we will learn about another very important concept related to the second moment of area, which is the parallel axis theorem. Well, you see, in life, things are not that simple. It would be nice if we had to calculate the second moment of areas for rectangle areas only. Unfortunately, we also have to deal with more complicated areas that can be divided into simpler elements. These are called, as you know, composite areas. Now, the challenge for this is that we need to calculate it about the centroid of the entire composite area in order to get a meaningful result for the second moment area for the entire section. So in other words, we will have to calculate second moment of areas for each element of the entire area, but then we will have to adjust these with regard to the centroidal axis of the entire section. So in order to do that, let's see how we can calculate the second moment of area about another axis which is parallel to the centroidal axis of the original area. So here we have a rectangular area. Its own centroidal axis runs through the middle of the area, but we do not want to calculate the second moment of area about the centroidal axis, but we want to calculate about a new axis, let's say axis VV, which in this case I selected it at the bottom of this rectangular area that has dimensions of B and D. So we will assume the same procedure by noting that the distance between the new axis VV and the centroidal axis is T. So that's the distance between these two axes. And we will select again an area element, very narrow element, having a thickness of dy, so infinitesimally small, and which is located at the distance y from the centroidal axis. We can now calculate the second moment of area with regard to the VV axis as integral from 0 to a of t plus y squared, all squared, dA. And now if we can expand the terms in the brackets, so we get t squared plus 2ty plus y squared times dA, all under the integral. And now we can break the integral into the three components. So the first component is a constant, so we can eliminate the integral sign, at squared. The second term, 2t, is a constant, so it can be factored out in front of the integral sign, integral from 0 to a of y dA. Well, guess what? This is the first moment of the area about a centroidal axis, so about that axis it will be obviously equal to 0. Plus a third term, which is the integral from 0 to a of y squared dA, which represents the second moment of the area about the centroidal axis, which is what we've learned about very recently. Therefore, if we sum up everything, the second moment of area about the parallel axis to the centroidal axis equals to the second moment of area calculated about the centroidal axis plus at squared. So the area of the element times the distance between the two axes squared. This is what is called a transfer term. So you transfer the result from one axis, which is the centroidal axis, to the new axis that is parallel to the centroidal axis. And therefore this expression, which is a fundamentally important expression, is called the parallel axis theorem. You have to remember this expression, you have to memorize, and you have to be able to know how to use it in solving various type of problems. So let's see how we can use this important expression in order to determine the moment of inertia about the v-axis. So first we will use IV, we will calculate IV by using the definition of the second moment of area, so integral over the area of y squared dA. So in the same diagram as before, then the second moment area with regard to the v-axis equals then to integral from 0 to d of y squared b dy. That's transforming the problem into a one-dimensional problem, and then equals to by cubed divided by 3 taken from 0 to d, or equals to bd cubed divided by 3. So this is by using integral calculation. Now, can we use the same, can you calculate the same by using the concept of the parallel axis theorem, the one that we've just learned? Well, let's see how we can use this concept now. So in this case, the moment of inertia about the v-axis will be equal to the moment of inertia of the rectangular area about its own centroidal axis, which is bd cubed divided by 12, plus the transfer term, at squared. So that will be equal to bd cubed divided by 12. The area is b times d. And in this case, this particular example, t equals to half d. So we have to square this up. So everything will be equal to bd cubed divided by 12 plus bd cubed divided by 4. And if we sum this up, we will end up with the same result, bd cubed divided by 3. So you can see a much simpler way of obtaining the same result, but using the parallel axis theorem rather than integral calculation. Now, what is very important here, and you will see in the next lecture when we will do an example, the transfer term at squared can become very large if the distance between the two axes, the centroidal axis and the new axis, is large, because this distance then will be squared, and then when we multiply this by the area, then you will end up with a very large term. So in order to maximize the moment of inertia, you would have to move a lot of area away from the centroidal axis of the entire section. But again, thank you very much for watching this lecture. And in the next one, we will do an example and we will see how we can calculate the second moment of area of a composite section.